So, what if we could build a computer that doesn't just crunch numbers, but actually learns the way a human brain does? Well, that's not science fiction. Today, we're diving into a totally revolutionary kind of AI that's trying to do exactly that. All right, here's what we've got on tap. First, we'll get into the whole idea of a computer with a brain. Then we'll unpack how these incredible brain-inspired chips actually work. After that, we'll see it in action with some amazing real-world examples. And finally, we'll talk about the challenges and what the future holds. So let's jump right in with part one, a computer with a brain. This really gets to the heart of things because it challenges how we've thought about computing for, well, forever. I mean, really think about that for a second. Imagine a machine that doesn't just blindly follow instructions, but can actually adapt, see patterns, and react to new things with crazy efficiency. That single question is the spark for this entire field. And the answer to that question? It's neuromorphic AI. It's all about building machines that are structured just like our own brains. So instead of rigid ones and zeros, these things have networks of artificial neurons and synapses. It lets them process information in a completely different and way more efficient manner. Okay, so for part two, how in the world do these chips pull it off? Well, it all boils down to a massive, fundamental shift in how we build a computer from the ground up. You know that feeling when you're stuck in rush hour traffic? That's basically what's happening inside almost every computer today. It's called the von Neumann bottleneck. Data is constantly being shuttled back and forth between the processor and the memory, creating this huge digital traffic jam. But neuromorphic systems, they get rid of the commute entirely. They process the data right where it lives. No traffic jam. And that is the secret sauce right there. By putting memory and computation in the same spot, just like the synapses in your brain, these chips get rid of all that wasteful data shuffling. It's a simple idea, but it's what makes them so incredibly powerful and efficient. So, how does this work in practice? The engine driving all of this is something called a spiking neural network, or SNN. Now, instead of processing a constant flood of data, these networks talk to each other using these little electrical pulses called spikes. And here's the kicker. They only send a spike when there's actually new information to share. It's event-driven, just like our own brains. Let's walk through it. Say a sensor detects a change, a new sound, a different image. That wakes up a neuron. The neuron fires off a spike of information to its neighbors. The whole system only uses energy when these little events happen, which means it learns with almost no wasted effort. It's not on all the time. It just wakes up when it needs to. And the result of all this is, well, it's a game changer. The amount of energy a neuromorphic chip uses is just a tiny fraction of what a normal CPU or GPU needs to do the same job. We're talking orders of magnitude lower. That has massive implications for everything from your phone's battery life to the power bill for giant data centers. All right, let's move into part three and see where this tech is actually making a difference. This is where all that cool theory starts to look like the future. Think about robotics. With neuromorphic chips, you can have robots that react to their environment with near human speed. They can figure out how to navigate a messy, unpredictable room or interact with people without needing to be programmed for every single possibility. They're literally learning from the world in real time. And in healthcare, wow, the potential is just mind-blowing. These systems could power the next generation of brain-computer interfaces. We're talking about prosthetic limbs that feel and act like a natural part of your body because they can interpret your own brain signals directly to help restore lost abilities. And this isn't just for labs and hospitals. This tech is coming to the devices we use every single day. It's called edge computing. Because they sip power, neuromorphic chips can run super smart AI right there on your phone or in a tiny sensor. They can recognize your voice or an object in a photo instantly without having to send anything to the cloud. So you see, this is so much more than just a small step forward. It really is a paradigm shift. We're not just making computers faster. We're creating a totally new pathway to machines that can learn, reason, and engage with the world in ways that feel profoundly, well, human. Okay, for our final section, let's look at the road ahead. I mean, this technology sounds amazing, but what are the roadblocks? And what's the long-term vision here? It's definitely not a straight shot to the finish line. There are some big hurdles. One is just pure scale, getting these systems to match the raw computational horsepower of today's best GPUs. Another is software. We need to create totally new algorithms that are built for these spiking networks. And finally, we've got to figure out how to plug this radical new hardware into the digital world we've already built. But the progress has been stunning. This whole idea was just a concept back in the 1980s. Today, we have actual chips in real devices. And if we look way down the road, say to 2050, we might even see these systems merge with things like quantum computing, creating hybrid machines with abilities we can't even really comprehend right now. And that kind of brings us to a final, pretty deep thought. As we get better at building machines that mimic the beautiful complexity of our own minds, we're not just building new tools. We're also kind of building a mirror. So the big question to leave you with is this. If computers can finally learn to think like us, what will they end up teaching us about ourselves?